All right, today's lesson, we're going to start looking at a graph's concavity, and this is going to involve using the second derivative. And I don't have another and. So concavity involves the second derivative. All right, so let f be a differentiable on an open interval I. So we would say the graph is concave up on an interval I if f prime, okay, so this is referring to the first derivative now, not the second derivative yet, but if f prime is increasing on the interval. All right, and then we would say the graph of f is concave down on an interval if f prime is decreasing on the interval. All right, and so this makes sense if you think about what a concave up graph looks like. So concave up is something like that, concave up like a cup. Okay, and so if we look at the slopes of this graph, so this is our first slope here. Let me do a different color. All right, and so very negative, and then it gets a little less negative until eventually we hit the horizontal one, which is 0, and then we go positive, and we get more and more positive each time. So those slopes are increasing as we travel along that curve. All right, and then a concave down function looks like that, concave down like a frown, and our f primes start very positive and get less and less steep each time until eventually we hit our horizontal tangent, and then we start going negative and more negative. So our slopes are decreasing as we travel along the concave down curve. All right, so how do we test for concavity? It's possible you can use this depending on what is given to you, but the usual test involves the second derivative. Okay, so we learned in our last couple days of lessons that we can tell a function is increasing if its derivative is greater than 0. So if f prime is increasing, the derivative of f prime is f double prime. So f prime is increasing when f double prime is greater than 0. All right, and so these are all three connected. If f double prime is greater than 0, then f prime is increasing, which means f is concave up. All right, so we can take out the middleman there. If f double prime is greater than 0, then the graph of f is concave up in that interval. All right, and then if f double prime is less than 0, that implies that f prime is decreasing. All right, f prime is increasing up here. And if f prime is decreasing, that implies that f is concave down. Take out the middleman. If f double prime is less than 0, then the graph of f is concave down. All right, definition of an inflection point. So an inflection point is where a function changes concavity. So that's the simple definition. Okay, we'll write out our answers down here. So a function f has an inflection point at c f of c if f double prime is equal to 0, or if f double prime is undefined. These are similar to critical points, except they involve f double prime instead of f prime. So we can't call them critical points because that's reserved. Sorry, I don't like the way I'm writing that. F double prime is undefined. There we go. All right, so we can't call them critical points because that's a phrase reserved for f prime only. So I usually just call them possible inflection points, because just having those two does not mean that it's an inflection point yet. So it's this or this, and then and. So this has to be true, and one of these things has to be true. F double prime changes sign from positive to negative, or negative to positive at x equals c. Or if you can't identify f double prime, maybe you'll be able to identify f prime. So f prime would be changing from increasing to decreasing, or from decreasing to increasing. Okay, so the reason we're talking about both f prime and f double prime is there are problems that are going to be on your FRQ that use f double prime, and other problems that you can only refer to f prime. Okay, so you have to know how to, this is all for your justification, how to write your sentence out to justify your answers. So sometimes you'll have to use F prime, so you'll be using increasing, decreasing with F prime. Sometimes you'll be able to use F double prime, and you'll use positive to negative on those. All right, just now realized that my webcam was blocked. The little latch switched to the wrong side, so hopefully you can see me now. Um, let's go to our next example, our first example. So we have a graph of f shown below. Okay, so I'm going to label this f of x right there, and then this is our x-axis down here. All right, and we have to state the signs of f prime and f double prime on the interval from 0 to 3. So we are saying just from here to here, what are the signs? Okay, so f prime is the slope of the graph. Okay, so just draw some mini tangent lines along here and tell me what the slope is. All right, well, all the slopes, all we have to do is the sign. So all those slopes are negative. All right, so f prime is less than 0. All right, f double prime is concavity. So look at the concavity, that is concave up. So that means f double prime is positive. All right, simple as that. So if you're looking at a function and they ask you about f prime, you're looking at the slopes of that function. If you are asked about f double prime, you're looking at the concavity of that function. All right, moving on. Okay, given a function, we're going to find all of this stuff. Okay, so A and B are from our previous lessons. C and D are from today. And then we're going to justify all of our answers and we're going to sketch a graph. Okay, and our sketch is going to be even better than the graphs we sketched yesterday. All right, so increasing, decreasing. This comes from f prime. Positive for increasing, f prime is negative for decreasing. Relative extrema also come from f prime. Concave up, concave down comes from f double prime. Inflection points come from f double prime. So when you read those words, that's what should pop into your head. Increasing, decreasing, relative extrema, first derivative, concavity, inflection points, second derivative. All right, just get used to doing that every single time. All right, so we take the derivative of our function. Our function is continuous. It's a polynomial. It's continuous. It's differentiable. All that good stuff. So we are able to do everything we need to do. Derivative is 4x cubed minus 12x squared. This derivative will never be undefined, so we just need to set it equal to 0. I'm going to take out a 4x squared. That'll leave me with an x minus 3. So I get x equals 0 and x equals 3 as my critical points. Put those critical points on a number line. Test a point in each region by plugging them into f prime. Okay, so -1. This out here, 4x squared, is always a positive because it's x squared. Multiplied by, and then whatever sign we get here. So if I go with -1, -1 minus 3 is a negative. Positive times a negative is a negative. Positive 1. 1 minus 3, also a negative. Positive times a negative is a negative. Positive 4. 4 minus 3 is a positive. Positive times a positive is a positive. So that tells us that f is decreasing, still decreasing, and then it changes to increasing. Okay, so this point right here is a relative minimum. This point right here, it is a critical point, but it is not a maximum or minimum. Okay, just because it's a critical point does not automatically mean it's going to be a relative extrema. Okay, the derivative must change sign at that point, and it doesn't here. So that's just nothing. All right, so we're going to write out our answers for A and B. So A, f is increasing on 3 to infinity. And we know that because f prime is greater than 0 on that interval. F is decreasing on. All right, so a lot of people ask, like, can I just say negative infinity to 3 because it's decreasing? Okay, I always caution against that. I think maybe that's okay, but because it's 0, it's a little unclear. Do we include 0? Do we not include 0? So I always separate them out. Okay, most of the answer keys I've seen on FRQs and the answer keys from our homework always separated out. So that's what I do as well. So I go negative infinity to 0 and 0 to 3. And we know that because f prime is less than 0 on those intervals. All right, part B. F, scroll down a bit. F has a relative min at 3, comma, and then I need the y value. So we're going to do f of 3, which is equal to 3 to the 4th power. That's 81 minus 4 times 27. 3 cubed is 27. 4 times 27 is 108. 81 minus 108 is negative 27. Yeah. All right, so 3, comma, negative 27. And I know that because f prime changes from negative to positive at that point. All right, so we've done A and B. Now it's time for part C and D. Part C and D come from the second derivative. So we're doing another derivative. F double prime is equal to, so take the derivative of your derivative. 12x squared minus 24x. All right, now we set that is also never going to be undefined, so we just need to set this equal to 0. I can factor out a 12x. That'll leave me with an x minus 2. And so I get possible inflection points at x equals 0 and x equals 2. Again, not going to refer to those as critical points because they are not critical points. They are possible inflection points. So another number line, 0 and 2. This time we are going to plug stuff into the second derivative, and this will tell us stuff about f. All right, so plug in negative 1, and I get a negative, and negative 1 minus 2 is a negative. Negative times a negative is a positive. Plug in positive 1, I get a positive. 1 minus 2 is a negative. Positive times a negative is a negative. Plug in 3, positive. 3 minus 2 is positive. Positive times a positive is a positive. All right, so that tells us about f, that f is, if the second derivative is positive, f is concave up. Second derivative is negative, f is concave down. Second derivative is positive, f is concave up. All right, these two are both inflection points. So I just put IPs. Remember, this number line is scratch work, so you don't have to be super specific. We are going to write out our answers in nice sentences just like we did over here. All right, so now it's time for that. C. F is concave up on negative infinity to 0 and 2 to infinity. And we know that because f double prime is greater than 0 on those intervals. All right, and then f is concave down on 0 to 2 because f double prime is less than 0 on that interval. Part D, f has inflection points at 0, comma. All right, and once again, I need the y values, so I'm going to do f of 0. And that's just 0. Zero's out both of those. And then I know I'm going to need f of 2 as well. So that would be 2 to the 4th power is 16 minus 2 cubed is 8 times 4 is 32. 16 minus 32 is negative 16. So f has inflection points at 0, 0, and 2, negative 16. And I know that because, all right, so what we wrote on the front page, I'm going to flip back real quick, is that your second derivative has to be equal to 0 or undefined, and it has to change sign. Okay, you do not have to say the first part. Simply the second derivative changing sign there. And unlike with maximum minimum it matters, right? A minimum is when it changes from negative, is when the first derivative changes from negative to positive, and a maximum is where the first derivative changes from positive to negative. For inflection points, there's no such thing as like a max inflection point or a min inflection point. It's just an inflection point, general term. Okay, so we don't even need to specify how it changed. All it has to do is change. That's it. Okay, so that's what we're going to write as our instructions here. F has inflection points at these two because F double prime changes sign. We don't care how it changes. It just has to change. So F double prime changes sign at those points. All right, so we've justified everything. We found everything we need to find. So now we can sketch our graph. So I have some room over here where I'm going to do that. I have 3 points that I found. I found 0, 0 is a point, 2, negative 16. So I'm just going to kind of mark negative 16 right there. And then 3, negative 27. So that's 16, 27, maybe right there. All right, so I know that I'm decreasing from 0 to 2. Okay, so I want to be able to see it on my screen. So I have my F prime list here. I'm gonna move the number line for F double prime up here. So it was 0 and 2, F double prime and F, and so it was positive and then negative and then positive. So I was concave up, concave down, and concave up. All right, so from negative infinity to 0, I'm decreasing and I'm concave up. So that's going to be something like this. Decreasing, concave up. All right, and then at 0, I'm still decreasing. So I'm still going to be going down, but I switch to concave down. So it kind of does one of those things and then switches to concave down until I hit this point at x equals 2. And then I switch back to concave up again, right there, like this. And then I remain concave up, but at 3, I go back to increasing. So I hit that and I come back up like this. All right, and so this point is where we had a horizontal tangent line. That's where our derivative was equal to 0. And this point also is a horizontal tangent line. It's just not a maximum or minimum because our function didn't change back to increasing there. All right, it remained decreasing the whole way. And then this is our inflection point where we go from our concave down to our concave up. And we're concave up the rest of the way. So you can see how we can create a pretty nice looking graph just by doing a little bit of calculus on these functions. All right, last examples down here. Sketch graph of a continuous function f with the given characteristics. All right, f of 0 is equal to f of 2. Both of those are equal to 0. Okay, so 0, 0 is a point, and 2, 0 is a point. All right, f prime is greater than 0. Okay, I'm going to make a number line. Looks like x equals 1 is an important number on our number line. F prime is greater than 0. So positive. That tells me that f is increasing. F prime of 1 is 0. Okay, so that's a critical point. And then f prime is less than 0, negative, if x is greater than 1. So that tells me f is decreasing. So this critical point looks to be a maximum. And then it tells me f double prime is less than 0. So that's concave down. And that's true for the whole graph. So the graph is always concave down. We increase up to 1. We decrease down the rest of the way. So I'm thinking a parabola here. So I'm going to put a point up here for x equals 1, increasing up to that point, decreasing the rest of the way. I'm concave down. I think I got it. All right, give the next one a try on your own. It's a little tricky, but I think y'all can figure it out. And then unpause the video and see how you did. All right, so we start the same way. We have the same 2 points, 0, 0, and 2, 0. F prime is greater than 0 on x is less than 1. So again, our number line starts the same way. F prime greater than 0, so f is increasing. And f prime of 1 is undefined this time. Okay, so that means that it still could be a critical point. It still it still is a critical point. But there's a couple different ways you could do this one. F prime is less than 0, so negative when x is greater than 1, so f is decreasing. All right, and then f double prime is greater than 0, so this is concave up the whole time. It's always concave up. Okay, so this one's a little tricky to draw. We know we have to increase up to 1, so I'm going to be starting low and going high, and I have to be concave up, not like this. That was concave down. So if I'm concave up, I'm going to go like this. Okay, and then I'm decreasing, so I'm going to start high, I'm going to finish low, and I still have to be concave up, so it's going to be something like this on this side. Okay, so that's always concave up. So now the question is, what's happening at 1? Okay, it's a critical point, so it's a maximum. But also, they didn't tell us, is f of 1 defined? All right, so I'm going to write that question over here. Is f of 1 defined? All right, that's a question that is ambiguous, and so there's 2 answers to this one that would be acceptable, given the information we have. So one answer would complete this. They would connect to each other. So connect, and that would be a cusp right there. And we would have a point. That would be our maximum point. Our function is continuous. I guess maybe that is the key part there. Sketch a graph of a continuous function f. So I lied when I said there were 2 answers because I forgot about this. Okay, so this is the only answer because our function has to be continuous. I'll go ahead and tell you about the other one I was thinking of. So another way that f prime could be undefined is if there had been an asymptote there, vertical asymptote. And then our functions would have gone to positive infinity from both directions. But that wouldn't work with this condition, that f had to be a continuous function. So glad that I remembered that. And we have our answer that these 2 will connect to each other. They will form a cusp, which makes our derivative undefined, makes that point a maximum still. We have our concavity. So there it is. All right, hopefully you enjoyed that video. I'll see you on the next one.